non-parametric test. So what is a non-parametric test? Well, it's a test that does not assume anything about the underlying distribution. So instead of that standard bell curve that we assume with parametric test, which is that definition, it's used when the data is not distributed normally, or we assume it's not distributed normally. So it can refer to a null category, since almost all statistical tests assume one thing or another about the properties of the source population. Now there's a variety of non-parametric tests. 3 of the most popular are the Kruskal-Willis test, which is used in place of one-way ANOVAs when we don't know aspects of that population. Another is the Mann-Whitney test, which is an alternative that we can use to the two-sample t-test. And one of the most common is the chi-squared test. Now a chi-squared test is a non-parametric test to compare 2 or more variables for randomly selected data. Well, what are the features of a chi-squared test? First, we have to consider the square of a standard normal variate. Second, we need to evaluate if the frequencies observed in these different categories vary significantly from the frequencies expected under a specified set of assumptions. Third, we'll have to look at determining how well an assumed distribution actually fits the data. Fourth, we'll use crosstabs or contingency tables. And fifth, it needs to support a nominal level measurement type. So, when using chi-squared test, generally we're doing a goodness of fit test, but sometimes we look at independence of 2 variables as well. So when we're doing a goodness of fit test, it's used to observe the closeness of a sample to match the population. So the chi-squared test, and chi is denoted as that x that you see squared, equals the sum of the observed count minus the expected count squared divided by the expected count. And this is k minus 1 degrees of freedom, which is the number of groups. The goodness of fit is really looking at how well the sample data will fit this set of observations. And if we're using the goodness of fit to identify the relationship between 2 attributes, you can see a few examples below of how we often will use chi-squared in these cases. So we might want to look at the creditworthiness of borrowers based on their age group and personal loans. We might want to look at the relationship between the performance of salesmen and training received. We could look at the return on a single stock and on stocks of a sector like pharmaceuticals, banking, etc. Or looking at different categories of viewer types and the impact of TV campaigns on those different viewer types. Now, when we're doing a test on the independence of 2 variables, and there's also other ways other than chi-square to do that, but chi-square is another aspect of following. It uses the same model, right? It's chi-squared equals the sum of the observed minus the expected squared divided by the expected. The difference here is the degrees of freedom. So while the degrees of freedom here is based on groups, k minus 1, here it's based on the number of rows minus 1 times the number of columns minus 1. And so 2 random variables are called independent if the probability distribution of one variable is not affected by the other. Now, tests of independence are extremely important, and like I said, this is a great test. There's also a variety of other tests for independence, but the majority of statistical and machine learning models assume independence of variables. They assume what's called orthogonality, or orthogonal, because we don't want the predictor variables, the cause variables, to impact one another when trying to predict the effect. We want to know how the variables are independently driving that criterion, that output, that target variable, that effect, that dependent variable. So, what would the use cases look like for test of independence? Well, if there's one categorical variable, if there's 2 categorical variables, you need to determine the relationship between those 2. If there's crosstabs, and we need to find out if there's a relationship between 2 categorical variables, and also if there's non-quantifiable variables, such as do employees in different age groups choose different types of health plans. So let's go through another example. The manager of a restaurant wants to find the relationship between customer satisfaction and the salaries of the people waiting tables. So she takes this random sample of 100 customers, asking each of them if the service was excellent, good, or poor. And she then categorizes the salaries of the people waiting as low, medium, and high. And her findings are shown in this table below. So you can see, overall, the majority of people say that service was good, a quarter say it was excellent, a quarter say it was poor. And the salaries of people overall showed 32, 27, 41. Now, let's assume the level of significance, p-value of 0.05. Here the null and alternative denote the independence and dependence of the service quality on the salaries of people weighted in table. So because we're doing a test of independence, it's the number of rows minus 1 times the number of columns minus 1. 3 minus 1 times 3 minus 1 equals 4 degrees of freedom. So under the null hypothesis, based on these calculations, you can see E11, which is this first column, first row, you have 26 by 32 divided by 100 equals 8.32, and these calculations are done for all the groups. Once those calculations are done to test the chi-squared for each variable, then we have to handle all those together. So we have the observed and expected 9.832 squared divided by 8.32, and we do that through all of the data. And we get a final value of 18.658. Now, when we look at that, of a probability of 0.05 with 4 degrees of freedom requires 9.48773, and that's that calculated value. So, because 18.658 is greater than 9.48, we can reject the null and accept the alternative. And so we find that service quality is dependent on the salaries of the people waiting. So let's say we wanted to perform this test in R, and let's consider a table that's a result of a survey conducted among students about their smoking habits. So this table has smoke variables, which record the smoking habits of student. And let's say we have heavy, regular, occasional, and never. And then let's say we have exercise variables, which records the exercise level of smoking, frequent, some, and none. So assuming a p-value of 0.05, test the hypothesis whether the smoking habits of students are independent of their exercise levels or not. So let's build a contingency table. We'll install and load the mass library package. And let's look at our table. So the table of survey smoke and survey exercise. And you can see the counts here that the majority of people who are heavy smokers tend not to exercise. But it looks like the people who don't smoke also tend not to exercise. And you can explore that and kind of look at patterns. But we'll move on. So let's use the chi-square test function for the contingency table and find the values for p. So when we run chi-square.test on the table, our output will be chi-squared equals 5.48885. And here we have 6 degrees of freedom, and the p-value is 0.4828. Well, if the p-value is 0.4828, that's greater than 0.05. So we fail to reject the null hypothesis. And so that means that the smoking habits of students are independent of their exercise level. So both parametric and non-parametric hypothesis tests are used to check whether the mean, variance, and proportion of the populations have predetermined values or if the values need to be defined. And let's discuss those in a little more detail.